So the first question is when is the planet going fastest in its orbit? And you all correctly chose, oh, when it's closer to the sun. All right, so that's that law of equal areas. So here's this elliptical orbit. Here's the sun. And there's that inverse relationship between centripetal force and velocity and radius. And so when you shrink that radius, you increase that velocity. Okay, so that's cool. All right. Now, the second, and everybody got that one right. So then on the second one, it's as the distance increases, what happens to the gravitational field? So this is that equation that we talked about yesterday, which is F equals big G m1 m2 divided by d squared. So because you're dividing by distance squared, as you increase that distance, the strength of that gravitational field becomes weaker and weaker and weaker and weaker and weaker because you're dividing by d squared. Now, here's what's going to be important. Because this is squared, okay, this is going to be one of the most important things you have to understand. Because this is squared, if you cut that distance in half, okay, so if you change that to d over 2 quantity squared, okay, and you're going to see a whole bunch of things that we're going to talk about today that are going to relate to this. So that's like saying that's d squared over 4. The 4 flips up, and you would increase the force, you would increase that gravitational field by a factor of 4. So if you cut the distance in half, the gravitational force goes up by a factor of 4. Now the other side of it is if you double the distance, if you make them twice as far apart, the gravitational field goes down by a factor of 4. So because this is squared, any small changes to that is going to make a huge difference. Okay, all right. So the poll question went well. I might have to try and resurrect that. Okay. Now, is the poll question now gone from your guys' screen? Okay. All right. So this is what I was telling Words earlier. Today is going to be good news, bad news day. I've got to go through and spend the next 50 some odd minutes deriving these equations. Okay. The good news is you don't have any homework tonight. Okay. So there's your trade-off. I have to talk, but you guys don't have any homework tonight. So I think that's a fair trade. All right. So here's what we had going yesterday. Let me make sure nobody wants in. Okay, we're good. Okay. So yesterday, here's what we worked through. Is that we said here was the Earth, and here was Riley, and we said that Riley had a mass of 50 kilograms, and we were treating her as a point mass and treating the Earth as a point mass. And one way to calculate that gravitational attraction, and this is important that you understand this concept of what a point mass is. It's like we took Riley and condensed Riley down to a single point. We took the Earth and condensed the Earth down to a single point. And so now we have 2 point masses that are separated by the radius of the Earth. And we came in here and we did this, and we said that's big G times Riley times the mass of the Earth, 5.979, times 10 to the 24th kilograms, and we divided that by the radius of the Earth squared, and we got about 490 newtons, okay? So this is the main idea. So when you talk about that gravitational force, what we're calling weight, this is one way that you can go through and calculate it. 50 kilograms times the mass of the Earth divided by the radius of the Earth squared. Okay, cool. Now, pretend that you don't know anything about these equations. Okay, you know nothing about these equations. But if you think back to the very first lab that you did, okay, and that was when you took the spring and you hung the spring, and you hung the weights from the spring, and we said, okay, on that very first day, I said to find the weight of something, you take the mass and you multiply it by G, okay? And if the other way that we could find the weight of Riley is that we could take 50 kilograms and multiply that by 9.8 meters per second squared, and oddly enough, we're going to get 490 newtons. Now, here's the whole kicker. Notice that these two numbers are the exact same. So this is one of the most important aha moments, okay, that exists in all of science, because so many things at this point became clear. So what we have right now, and this is one of the most important things that they discovered in all of this whole concept from Newton's work, is that if you look at the two ways to calculate Fg. So one was we're going to take the mass of Riley, and Riley, I don't want you to take this personally about what's going to happen, either one of you, okay? Pick the Riley of your choice. This is going to be the mass of Riley times G is going to equal big G times the mass of the mass of whichever Riley you want, times the mass of the Earth divided by r squared. Now, here's what's going to happen to Riley, okay? Riley's going to drop out of the equation, and that's going to happen to anyone, okay? Me, you, doesn't make any difference. The mass of the object is going to drop out of the equation. So what you're left with, and this is the first of the big equations, you have little g equals big G, mass of the Earth over r squared. So if you look on your equation sheet, okay, right over here, you've got this equation right here that little g equals big G m over r squared. So let's talk about what this is. Your little g, which I always thought if I was going to be like a rapper, that would be like my rap name. Give it up for little g, okay? So you got little g, that's going to be your gravitational acceleration, okay? Okay? So this is going to be, and this is going to be important, this is the mass of the planet, okay? This is not what you're dropping, okay? So this is what you're falling towards. So this isn't like the 1 kilogram mass. This is whatever planet you're talking about, or moon, or whatever it is, okay? So if you were to take big G, plug in the mass of the Earth, plug in the radius of the Earth, you would get 9.8 meters per second squared. If you're on the moon, okay, you would plug in the mass of the moon, the radius of the moon, and you could calculate the gravitational acceleration on the moon, okay? So here's what's important. At this point, the work of Galileo now makes sense. So Galileo took, a 1 kilogram mass and let's say a golf ball, and he dropped them. And they both accelerated at the same rate. So here's what's important. The reason that works is because the mass of whatever's falling doesn't matter. Okay? That's not part of the equation. The only thing that determines this gravitational acceleration is the mass of the planet, not the mass of what's falling, the mass of the planet, and how far you are from the center of the planet. So what that means is here's the Earth, and this is so not to scale, but let's say there's Mount Everest, okay? So if you're on top of Mount Everest, you're going to be dividing by a bigger radius because you're going to be farther from the center of the Earth. So on top of Mount Everest, little g is a little bit less than what it is right here. Even if you go to Denver, Colorado, if you go to Denver, Colorado, slightly higher altitude, the gravitational acceleration in Denver is a little bit less than it is right here, okay? So this is one of the key things that you have to understand. This is why everything accelerates at the same rate, because the mass of whatever is falling doesn't determine the gravitational acceleration. Only the mass of what's falling and the radius, okay? What? Okay, hold on. I got to go find something in the chemistry department. They can't find it. I'm going to be right back, okay? So stay put. I got to go help the chemistry department. All right, we're back. Sorry about that. They couldn't find the chemical, and it was right there in plain sight. Okay, so here's the deal. So here's how we can actually use this equation. So one of the first things that they did when they got to the moon is that they set up, when they landed on the moon, they set up a pendulum, okay? And you would think, why would you go all the way to the moon to set up a pendulum? Well, here's the reason why. The period of a pendulum is 2 pi times the square root of L over G. So what they wanted to do was figure out, well, what's the actual gravitational acceleration on the moon? So they set up a pendulum, and they timed the length of the swing. They knew the length of the pendulum, so then they were able to solve for G. Oh, okay, right. Now, once they had that little value of G, then they could go little g equals big G, mass of the moon, over r squared. So, once they knew what little g was on the moon, and we've known the radius of the moon for quite a while, then we were able to solve for the mass of the moon. So one of the things you'll see is that there's 3 big equations that we can use. How we figure out the mass of the Earth, the mass of Saturn, the mass of the Sun, whatever it is. It isn't like, hey, let's go find the mass of Jupiter. Oh, okay, right. We're going to grab Jupiter, we're going to stop it in its orbit, and we're going to set it on a scale, and we're going to read the scale, and it's going to say, oh, Sproles, you went back in. Ah, Spain.
They kicked him out, he said.
Huh?
He said that the Zoom kicked him out.
Well, as well it should. Okay. Sproles, you're back? Okay. I think it's that New York Yankees emblem behind you. I think that's
my
it.
internet crashed for a second, but it's good now.
Okay, all right, fantastic. Glad to have you back. So, when we're trying to find the masses of these planets, we can't stop them and put them on a scale and go, oh, here's the mass of Saturn. Oh, here's the mass of Jupiter. We have to look at the influence that it has on objects that are orbiting around it, or the gravitational field that it creates. So, if you look in solving for this, so you take little g r squared divided by g equals mass. So this is what we were able to do even on terms of the Earth. So Henry Cavendish, he was the guy that actually came up with the numeric value of little g. Okay? Newton just proposed the equation. Newton actually never found the numeric value of this. A guy by the name of Henry Cavendish did. So once Henry Cavendish knew this value, and we knew the gravitational acceleration on the Earth, and we knew the radius of the Earth, this is how we found the mass of the Earth. So Henry Cavendish's claim to fame was that he was the first person to weigh the Earth. Okay? So by finding this mass, he was able to determine the mass of the Earth. Then once you had that, you could do a whole bunch of different things. You could find the density of the Earth because we knew the volume of the Earth. So that opened up a whole can of information and research that we could begin to do. So here's what I want you to get out of this. Okay? This is the gravitational acceleration caused by a planet. Okay? This is the mass, this is the radius. Now, here's what's important, and you're going to see this on all 3 of these equations that we're going to come up with. This radius is based upon a center, from the center of that planet out. Okay? Any radius that you're going to use is not from the surface. Okay? Any radius is from the center of that planet out to that point. Okay? Listen to me. It's from the center out. It is not the surface distance. And that whole idea comes from the idea that you're going to treat the Earth as a point mass, and it's just like I've got a point mass here, and I've got another point mass out here. So listen to me. Any radius has to be from the center. The other thing that you're going to see is that that radius has to be in meters. We cannot work in astronomical units. We cannot work in kilometers. This thing only works with meters. And here's the reason why. So any equation has to work in terms of dimensional analysis. So if you look at that, little g equals big G mass over r squared. So, and this is one of the things I'm going to make you do on the test, okay? I'm going to tell you right now, on the test on Monday, you're going to have to do a dimensional analysis, maybe on a question like this. Here's the process. You're going to go big G, oh, that's newtons, meters squared over kilograms squared. You've got a mass in kilograms, and then you've got a radius in meters that's going to get squared, okay? So this is flashbacks to dimensional analysis back in Unit 1. So you've got newtons, meters squared over kilograms squared, times kilograms, meters squared. If you're not sure of the units on big G, look on your equation sheet. It's in the top left corner, okay? That's where the units are for big G. So if you look at what's going to happen, we're going to cancel out those meters squared. We're going to cancel out one of those meters. So we have newtons over kilograms at this point. This is what we have left. Now, here's the kicker. Remember, newtons are the same as kilograms meters per second squared. So I'm going to come in here and put kilograms meters per second squared divided by kilograms. The kilograms cancel out. I get meters per second squared. That's what my gravitational acceleration is measured in. So this is the type of thing that you've got to be able to do on the test. Okay? Is I'm going to promise you, on this test, I'm going to pick an equation like this. I'll tell you which three I'm going to choose from. This is going to be one of them. And I would expect you to be able to prove that you get the right units out of this. Now, because this is r squared, okay, the same thing is going to happen. So let's say that I'm going to take the Earth and I'm going to double the radius of the Earth, but I'm going to keep the mass the same, okay? So in other words, we're going to take the Earth, okay, and we're going to make the radius twice as big, and I want to see what's going to happen to little g, okay? So I'm going to take little g times the mass of the Earth. That's going to stay the same. We're going to keep the mass of the Earth the same. But then we're going to double the radius, but that's going to get squared. So then I'm going to have little g, mass of the Earth, over 4r squared. That becomes 1/4 of big G r squared. So if we could take the Earth and double the radius, the gravitational acceleration would become 1/4 as much, which would make it like 2.5, which is kind of similar to like the gravitational acceleration on the moon. It's a little bit more than what's on the moon. So it's kind of a cool idea to think about. Oh, okay, right. So imagine me dropping this ball and it's falling like a fourth, the acceleration is a fourth of what you're used to. You could jump 4 times higher, okay? Playing golf would be pretty cool, right? You could drive that ball a mile, okay? Especially if you didn't have an atmosphere, which would be tough if we lost our gravitational field as well. Okay, so again, you'll notice the theme here, you have r squared. If you double it, it goes down by 1/4. If you shrunk the Earth by 1/2, the gravitational acceleration would go up by a factor of 4. Okay, so we're good with that. Now, we're going to talk about satellites. So here's the Earth, and here's the satellite. And let's say that it's orbiting 140 kilometers above the surface of the Earth, and that's about typically where satellites orbit, okay, in a near-Earth orbit. And let's say that this is going to be the satellite Maddie, okay? So here, Maddie is the name of our satellite, okay? So Maddie is orbiting around the Earth. So here's the first big question, okay? Maddie's a satellite. Maddie has mass. Maddie doesn't want to travel in a circular path. Maddie wants to travel off in a straight line because of Newton's first law of motion. So if that's the case, there has to be some force that's acting inward to keep this satellite in orbit. Okay, and again, you have three options. It has little wheels and it's driving around on a track. It's really not an option. We tie a string and we swing it around the Earth, and that's what keeps it in orbit. Okay, really not practical. or we let gravity do the work. Oh, let's go with that option. So here's going to be the most important idea when you talk about satellite motion or motion through the planets, whatever it is, anything that's in orbit. And this is what we talked about in terms of the Mercury lab. That the gravitational force is going to equal the centripetal force, because that's the only game in town. Okay, that's the only thing that you have available to you to make this thing orbit. Is the gravitational field has to equal that centripetal force. That's it. There is nothing else. There's no strings. There's no friction. There's nothing else. So help me. This is the first thing that you have to understand, and if you don't get this, nothing else is going to make any sense. Okay. So you have to understand that the gravitational attraction between that satellite and the Earth is what's creating that centripetal force. Now, we'll start with the relatively simple one. So there's two ways you can calculate centripetal force. We're going to use mv squared over r, and this is going to be the mass of Maddie. Okay? All right? So this is going to be the mass of the satellite, which we've named Maddie. So Maddie the satellite is orbiting around the Earth. Okay? It's going to take a certain amount of centripetal force to keep Maddie the satellite in orbit. Okay? This is what we can find right here. Now, that has to equal big G times the mass of Maddie times the mass of the Earth divided by r squared. Okay? So these two things are equivalent. So that gravitational attraction between Maddie and the Earth is what's creating the centripetal force to keep her moving. Okay? So this is one of the main ideas that you have to get out of this. Now, don't take this personally, Maddie. Okay? Don't take this personally. Well, what's going to happen is that Maddie is going to drop out of this equation. Okay? So the mass of the satellite doesn't matter. Okay? Just like the mass of whatever I drop doesn't impact the gravitational acceleration, the mass of the satellite drops out. So what that means is that this is going to go away. So on every problem, okay, in every problem I'm going to give you with the satellite or the lunar command module or the Earth going around the sun, whatever it is, I will never give you the mass of the satellite because it doesn't matter. Just like when you all took the acceleration test and you did the ball off the building and one went up and the other one was dropped, okay? I never gave you the mass of the ball. You know why? It doesn't matter, okay? So I will never, ever, ever give you the mass of the satellite because it doesn't matter. You can't plug it into the equation if you try because it drops out. So here's what we've got. We've got big G times the mass of the Earth over r squared equals v squared over r. So now, I hate fractions, so I'm gonna multiply this over. So because I want to get v by itself, so I'm going to multiply this side by r. Okay, so that's going to cancel out one of those, and then I'm going to take the square root of that. I'm going to get big G mass of the Earth over r is going to equal my velocity. So what this is this equation over here to the left of the one that we just figured out with a little g. So this is on your equation sheet. Don't memorize it. It's there. You just have to know how to use it. Hold on. We got a latecomer. All right. Dalen's in. Okay. Now, again, this doesn't have to be the Earth. If you're orbiting the moon, you're talking about the lunar command module orbiting the moon, this would be the mass of the moon. If you're talking about a moon of Saturn, this would be the mass of Saturn. So this mass is just whatever is at the center of the orbit. This is not the mass of what is orbiting, okay? Just like I'm never going to tell you that a satellite is made out of aluminum, okay? I'm never going to tell you that because it doesn't matter, okay? I'm never going to give you the mass of the satellite because it doesn't matter. It drops out of the equation. So, So what we're going to try and do is we're going to figure out what the velocity is of this satellite. So here's your setup. So here's the Earth, okay? Here's Maddie the satellite, okay? And Maddie the satellite is orbiting at a distance of 140 kilometers above the Earth. Now, I'm going to go get an apple. I need a visual. Okay, I happen to have an apple. So, to give you some perspective of scale, imagine this is the Earth, okay? Our atmosphere is the same thickness as this red layer on the outside of the apple. So if you could model this as the Earth, what keeps us safe and able to exist as a species is the outside layer of this apple on a relative scale. That's it, okay? So that's all the thicker this atmosphere is. So it's kind of cool, but we don't have much. The point is that it's a pretty thin layer. So on a relative scale, that 140 kilometers would probably be about the thickness of my pencil above the apple, okay? So there isn't anything magic about space. We just have to get above our atmosphere because we can't make things orbit as fast as they need to go within our atmosphere because of frictional heating with the nitrogen and oxygen molecules. And things heat up. So what we have to do is we have to get them high enough to be outside of our atmosphere. If we didn't have an atmosphere, we could make things orbit at the same altitude that airplanes fly. Okay? You could look up and go, oh, here's the space station. We could just have to clear the mountains. That's all we'd have to do. So don't think there's anything magic about space. The only thing magic about space is that we don't have that frictional drag created by our atmosphere. So that 140 kilometers isn't that far on a relative scale. As a matter of fact, that's less than the distance to Kansas City, and that's one of the problems that we're going to do. Okay, so I'm going to try and figure out how fast this thing is going. So I have big G, mass of the Earth, divided by R. Now, here's what you're going to do wrong. You mark my words. You're going to see this 140 kilometers, and here's what you're going to do. You're going to go, oh, there's my radius, and you're going to plug in 140, and you're going to pay no attention whatsoever to the units. Now, you all sit there, I can't even see you, so I know you're lying, and because most of you have your cameras off, okay, and you all are going to go, oh no, Mr. Burkham, we won't do that. We promise. You lie, okay, you lie. I promise you that's what you're going to do. Anytime you see big G, this is the absolute poster child of the MKS system. You have to be in meters, kilograms, seconds. That's the only way this thing works, is if you're in meters, kilograms, seconds. So, not only do you have to change that into meters, multiply by 1,000, don't divide by 1,000 and say the radius is 0.14 meters, okay? Because 0.14 meters would be like this distance right here, okay? That would be 0.14 meters if you divided by 1,000. You are not going to orbit 0.14 meters above the Earth, okay? It's not going to happen. So, we're going to multiply by 1,000. Now, somebody get out a calculator because I'm just making this number up. So I'm going to need somebody to help me out with a calculator. So we have 140,000 meters, okay? So that's this distance from here to here. Now, what else do I need to do to be able to use that as my radius? What do I have to add to it? Sproles. What do I have to add to that distance to be able to use it as the radius?
I have genuinely no idea.
Okay, Sproles. Where do we measure the radius from?
The center.
Right, so the 140,000 is this distance here, right? So what do I have to add to it?
The extra distance out.
Yeah, the radius of the Earth, right? Because here's the Earth, so we have to have the distance from the center of the Earth out to that satellite, okay? So the 140,000 is just this distance right here. We've got to add to that the radius of the Earth itself, because it has to be a center-to-center distance. So this is where I'm going to need some help with somebody with a calculator. So somebody take 140,000, which is 1.40 e to the 5th, and then we're going to add that to the radius of the Earth, 6.3713 e to the 6th. When you add these numbers together, do not round your answer. Keep all of these digits. We're going to round when we get to the end, okay, when we actually calculate that velocity, okay? So when you do this, don't round it. Keep the digits round when you get to the end, okay? So, somebody give me a shout out. Somebody take 1.4 e to the 5th and add that to the radius of the Earth. What do you get?
I got 6.5113 e to the 6th.
E to the 6th meters, okay? Okay. Now, I actually want the numeric answer in just a second, but not right now. Okay, I don't want to know. I don't want to know what the answer is. So, what I want to do, what we talked about yesterday, I just want to get an order of magnitude. I want to get an idea of what the exponent is going to be on this calculation. Okay, I just want an idea. So, I got 10 to the negative 11th times 10 to the 24th. So that gets me 10 to the 13th, okay? I take 10 to the 13th, I divide that by 10 to the 6th, I get 10 to the 7th. But then I'm going to take the square root of that. So what you'll see is that all velocities orbiting the Earth, okay, or orbiting the Moon, are always going to be 10 to the 3rd meters per second, okay? That's always the range that they're going to be in. So if you ever calculate a velocity and you get something other than 10 to the 3rd, you have done something wrong. You've probably forgotten to take the square root. You didn't convert a radius into meters. You left it in kilometers. You didn't add in the radius of the Earth, something like that. Certainly, if you ever get a velocity approaching the speed of light, which is 10 to the 8th, you have done something wrong. And now, I give this speech every year, and you all sit there and go, Mr. Burkamp, we'll never get anything close to the speed of light. Every year, somebody calculates a velocity faster than the speed of light. It happens every year. One year, I might quit if this ever happens. If you guys do this, and we go to this entire unit, and nobody gives me a velocity close to the speed of light, I just might call it good and say, hey, I've perfected my teaching technique, drops the microphone, walks off the stage. We'll see. All right. Now, somebody actually crunched the numbers. So this is why it's handy to have these numbers stored in your calculator. This is big G. Here's the mass of the Earth. That way you don't have to punch them in every time. Okay? So again, I'd store 3 things in your calculator. I'd store big G, I'd store the mass of the Earth, and I'd store the radius of the Earth. Okay? That way you don't have to punch them in every time. So, Caden, did you get me an answer?
I got 7.83 e to the 3rd.
Beautiful. Okay? Now, let's talk about how fast this is. Okay? And let's talk about this whole concept of what an orbit actually is. So, we're going to get back to this in just a second. So, here was Newton's thoughts on what happens when something's in orbit. So imagine that you have a tall mountain and you've got a cannon and you're going to shoot a cannon ball out of a cannon, because that's what cannons do. And we're going to shoot a cannonball out of this thing, okay? And it's going to go like this, okay? So if that's cool, well, let's put in some more gunpowder and see what happens. Oh, okay. So then we're going to shoot it, and then it's going to go something like this. It's going to go further. Now, imagine that we put in even more gunpowder. And then it's going to go something like this. And then it's going to come back around, and it's going to hit the back of the cannon. Okay? So when something's in orbit, okay, you have to understand what happens when something is in orbit. When something's in orbit, it isn't because it's in zero gravity. If it was in zero gravity, you would shoot the cannon, it would just go off like this. When things are in orbit, it's because of the fact that they're in a state of free fall around the Earth. Now, if you're at the surface of the Earth, okay, and here I will not expect you to know this, you just need to know the concept. If you travel out 8,000 meters, the Earth curves out from underneath you 4.9 meters, okay? So 8,000 meters is about 5 miles, okay? So what that means, and here's the significance of this 4.9 meters. So if you look at the equation, the distance equals 1/2 AT squared plus V naught time. So when I drop this golf ball, okay, if I could let it fall for an entire second, and I'm going to drop it, so V naught is going to go to 0. So we're going to have 1/2 times 9.8 meters per second squared times 1 second squared. And I want to get 4.9 meters. Okay, so here's the significance of this number. So if you could drop something and let it fall for an entire second, it would fall 4.9 meters, which is about twice as high as the ceiling. So you can kind of get a visual of what's happening. So for every 8,000 meters that you travel, the Earth curves out from underneath you 4.9 meters. So what that means is if something's going to be in orbit, it has to be traveling at 8,000 meters per second. Because if it travels 8,000 meters per second, then it's going to fall the same radius that the Earth is falling out from underneath it. Now, to give you some perspective on how fast that is, okay? Imagine that you're at 53rd and Mays Road. Okay, you're at 53rd and Mays Road. So you're going to go to 45th, 37th, 29th, 21st, and 13th Street. So you're going to go from 53rd and Mays Road all the way down to 13th and Mays Road in 1 second, okay, which is about 5 miles per second. That's about how fast you have to be going to put something into orbit. So, and this would be cool if I could do this. So you can kind of get an idea of what happens. So if I take this golf ball and I just give it a little bit of velocity, okay, boom, right, it's going to travel a certain distance before it falls. If I throw it faster, okay, right, oh, wow, that completely hit an open door and just went completely KY. Okay, and now it's over in the chemistry room. Okay, it's gone. Okay, so this would be the ultimate cool demo to do. Imagine that imagine I'm going to take this Zoom meeting outside, and I'm going to throw that golf ball, and it would take, and later on you'll see this takes about an hour and a half to get back. So I can throw that golf ball, walk away, then about an hour and a half later, that golf ball would come back to that same spot. So here's what I want you to get. When you see the International Space Station or whatever, you see people floating around in space. They are not in zero gravity. They are just in a continuous state of free fall around the Earth. That's all that's happening. They are not in zero gravity. Okay, so Caden, here's your job for now. Remember that radius because we're going to need it again later. So Caden or somebody, remember this number. 6.5113 e to the 6th. Okay, we'll get back to that number. So here's the deal. So we've got this equation little g equals big G mass of the Earth over r squared. We just came up with V equals big G m mass of the Earth over r. Okay? Now, if you make the radius bigger here, little g becomes smaller. If you increase the radius in this equation, the velocity becomes slower. So, what this means is if you bump a satellite into a higher and higher orbit, it's going to go slower and slower and slower. So the further you are from the Earth, the slower the satellite's going to move. Okay? It's a key thing to remember. Now, here's the last big equation that we need to come up with. And we're still going back to the idea that centripetal force equals my gravitational force. Now, the other way that we can calculate centripetal force would be the mass of the satellite Maddie times 4 pi squared r over t squared equals big G mass of Maddie, mass of the Earth over r squared. Okay? So all I did was substitute in that other way to calculate centripetal force. That's all I did. Okay? I just put in a new way, that second alternative to calculating centripetal force. Now, oddly enough, here's what's going to happen. No offense, Maddie, but Maddie's going to drop out of the equation. Okay, so Maddie's gone at this point. So what we're going to do is we're going to cross multiply. Now, this becomes the pirate's favorite equation because I get 4 pi squared, wait for it, and then I get r cubed. All right, shiver me timbers, I get r cubed. So now I've got r cubed equals G mass of the Earth times t squared. So what I did, okay, so that's this equation down here. So this is this last equation. Down here you have big G m t squared 4 pi squared r cubed. So this is the last of the planetary equations. And again, this is like the poster child of the MKS system. This r has to be in meters, and it has to be from the center of the Earth. This mass has to be in kilograms, and that t has to be in seconds. Okay? That's the only way this thing works. And here's what has been my experience over the years. Y'all don't struggle with radius being in meters. That's cool. You don't struggle with mass being in kilograms. You don't struggle with that. What you struggle with is this t. Okay? Because typically when the information that you're going to be given, this t is going to be in hours, it's going to be in minutes, it's going to be something like that. And what you're going to forget to do is change t into seconds. It's the most common mistake that's made. So right now, begin to plant in your minds that if you're going to use big T in this equation, it has to be in seconds. All right? But I promise you, on every problem that you're going to deal with this T is not going to be in seconds. It's going to be in hours, it's going to be in days, it's going to be something else. This is not Kepler's third law, where you can let T be anything that you want it to because it's a ratio. So anytime you're seeing big G, make a mental note and say, oh, this T has to be in seconds. That's the only way this thing works. Okay, that's the only way it works. All right. So the reason that I gave you this equation in this format, because this is like the Swiss Army knife equation. I can solve for 3 different things here. I can solve for a radius, I can solve for t, I can solve for the mass of whatever I'm orbiting. So this is why I gave you this equation in this format. Because if it's like this, then it becomes very, very easy to solve for any variable. Radius, mass, t. So what we're going to do is that we're going to look at the problem that we just had. So we want to figure out how long it's going to take satellite Maddie to go around the Earth. So we're going to try and find this value of t. Okay? So I'm going to solve for t, right? So I'm going to divide this over. So I'm going to have 4 pi squared r cubed divided by big G, mass of the Earth, that was a horrible M, and then I'm going to take the square root of that, and that's going to get me T. Now, sometimes when you see this equation in a textbook, or if you look at this equation in line, like if you Googled it, a lot of times you'll see it written like this, where they pull out this square root of 4 pi and they'll put that 2 pi out here on the outside. So if you want to work this equation like that and put the 2 pi on the outside, I don't care. You can leave it underneath the radical. I don't care. It doesn't make me any difference whatsoever. Okay? It makes me no difference. But here's what you're going to forget to do. You're going to forget to cube that radius. Okay, that's the most common mistake that's made. You're going to forget to cube that radius. So, we're going to do this with the numbers that we just had. So, we're going to try and figure out how long it's going to take this to go around. So, I'm going to have 4 pi squared. What was that radius? Hold on. 6.5113. Okay. Now, again, let's just look at this thing in terms of order of magnitude. Let's just get an idea of what we should get. So I got 10 to the negative 11th times 10 to the 24th. So down below, I have 10 to the 13th. Okay? Now, up here, I've got 10 to the 6th, but that's going to get cubed. So that's going to get me like 10 to the 18th, okay? And then I'm going to multiply that by 4 pi squared, so that's going to basically make this up, the one upstairs be 10 to the 19th, okay? So I've got 10 to the 19th divided by 10 to the 13th, so that's going to get me 10 to the 6th, and then I'm going to take the square root of that, and I'm going to get 10 to the 3rd. So here's what's important. Your orbital period in seconds is typically going to be 10 to the 3rd. So this makes this easy to remember, okay? You don't have to remember different things. So when you get done, your orbital period in seconds for a near-Earth orbit is going to be 10 to the 3rd. Your velocity, we said, was also going to be 10 to the 3rd. So when you're doing near-Earth calculations of period or velocity, the period in seconds, your velocity in meters per second should both be 10 to the 3rd. If you're not getting those numbers, you've done something wrong. Okay, so you don't have to remember different values for period or for velocity. And whether it's the moon, the earth, it doesn't make any difference. They're going to be 10 to the 3rd. Okay? So, now, so somebody take a calculator, if you would please, Caden or somebody, and actually get me this number. And again, here's what you're going to forget to do. You're going to forget to square this pi, okay? Or you're going to be so happy about getting an answer that then you're going to forget to take the square root of it, and then you're going to leave it like 10 to the 6th or 10 to the 7th, whatever that comes out to be. Because you're going to be so excited, it's like, oh, I got an answer, score! And then you're going to forget to take the square root of it. So, Kate, or somebody, give me an answer.
I got 5.23 e to the 3rd.
5.23, so 5,230 seconds. Okay, which is what we said. It should be something times 10 to the 3rd. Now, Caden, do us a favor. Take that and divide it by 60 so we know how many minutes that is.
87.1.
Okay, 87.1 minutes. So about an hour and a half. So what's going to happen is that satellites, and this is like if you're in the International Space Station or something like that, that's typically about how long it takes for something to orbit in a near-Earth orbit. It's about an hour and a half. But again, look at what happens. if you bump that satellite into a higher orbit, especially since it's r cubed, the higher you go, the longer that's going to take to go around. So, one of the problems you're going to have on your assignment, which is not, we won't talk about the assignment until tomorrow, is the concept of a geosynchronous orbit. So in a geosynchronous orbit, what happens is that, let's say that you have the satellite Apple, and you want to park a satellite so it's always directly above Mays, Kansas. So if I want this satellite to always be above Mays, Kansas, then I need that orbital period to be 24 hours, because it's going to take Mays 24 hours to go around on its axis. Hold on. I just dropped the Earth. Sorry about that. So, but if I put it in a near Earth orbit, then it's going to go around every hour and a half. So the farther that I park this satellite out, the faster, the longer it's going to take for it to go, and the slower it's going to go. Okay, so you don't have any homework tonight. We got through these equations, so here's what's going to happen. So tomorrow, I'm going to show you how these equations work and give you a bunch of examples. That's going to be tomorrow, which is going to be Thursday. We're going to spend the day Friday kind of finishing up this assignment. This assignment is not going to be due until Monday of the test day, unless you want to get it to me early and have me grade it and get it back to you. And then the test is going to be on Monday. So one of the things I'm going to ask you is how you want to take the test, and you have three options. You can either come into school on Monday and take it. I can send you a PDF file and you can print it out. Or if you don't have access to a printer and you want to take it at home, I can arrange for you to come up to the school and pick it up in the office. So eventually you're going to need to decide how you want to take that test. And again, I cannot emphasize this enough. Do not feel under any obligation to come up here and take this test. If you want to take it at home, that's fine. Take it at home. Okay? It's not a big deal. All right, we're out. It's 9:30. We will see you all tomorrow morning. And yes, Riley Words, you have no homework tonight. So, be happy. All right, see you kids.